go. All right. Yeah, most people think it's a 4 day weekend, so the day before the 4 day weekend should also be part of the weekend. No, that is not true. All right. So I'm gonna get started here. All right. First thing first, do we have any questions about this particular topic? I finished the recording. I hope you guys watched both video recording. Part one is in class. The second part is also uploaded to YouTube. All right. Well, I can see that some people might have not found it. Okay. But I did say that I would record it. I guess on my way, walking out. Um, but it's okay. Do we have any questions? Did I say anything about recording the second half of the lecture and then just post it online? Yeah. No. Alrighty. Well, I can just play that second part of the class recording and just you guys have to watch it here and I'll just kind of walk outside. Or we can just kind of go over that, you know, like in class. All right, so we're gonna go over that in class. And I cannot remember where we stopped. I believe we were working on the program. I think we got all the bit pattern checked out, right? All the bit pattern worked out. Is that correct? Okay, let me get my own stuff. Okay, I have recording, so that's why I can find out where we stopped last time. Okay, let me check it here. Mm, Yes. Okay. So, all right. So this is my what I have captured from last time, I believe. Nope, that is no. That looks like a part of it, but not the entire thing. All right. Well, I can just do the whole thing. Okay. So I think it'll be fine. I can just redo the whole thing. All right. But I do remember, approximately how much we went through. So I don't have to go through the entire thing, and we can start with this number here. Okay. All right. So let me get rid of the irrelevant stuff. Okay. So I think by the time we left the class, by the time the fire alarm went off, I already came up with this binary representation. Think so? Yes. Okay. So I'm gonna start with that. Okay, because it is kind of important that you guys keep track of the notes too, to know where we stopped last time and at least review up to that point. All right. So and then I talk about how this thing is the same thing as this thing times 2 to the power of 0 because 2 to the power of 0 is just 1. And then I think we shifted the binary point 5 times to the left-hand side, so it becomes 1.011100001 in base 2. And then every time we move the binary point to the left-hand side, we have to increase the power of 2 by 1. So that means we have to increase this to 2 to the power of 5. Okay, so do you guys still vaguely remember that? Because I remember how many times we have to shift the binary point. Okay, so that the number may not be the same. I think it is not the same because I think we were working with a negative number. Yes, and that's how we worked out the sign bit should be a 1 instead of a 0. But I don't have any recollection of that part. Let me see if I can find another mouse pad window here. So that's 12. I got it. Okay. So I can work with exactly the same number. I pull out the wrong screen. All right. So this is the correct screen. There we go. Um okay. I'm pretty sure that part we haven't really talked about yet, so we can start with this part. I think the number that we were working with is negative 58.375. Pretty sure about this one. Okay, we did all the we did the binary point shifting. So instead of having the binary point to be here, we shifted it 5 times to the left hand side, so it ends up here. So this way we have a mantissa because 1.11010011 in base 2 is a proper mantissa. Okay, so and I do remember that I talked about, what is the requirement for a coefficient to be called a mantissa. It has to be greater than or equal to 1. It has to be at least 1, but it cannot be the base itself. It has to be less than the base, which in this case is base 2, so it has to be less than 2. Okay, so I'll be okay with that. And then we worked out the bits corresponding to the fractional part of the mantissa, and I think that's probably where the alarm went off. Is that correct? Okay. Since you guys are not sure, I will double check with my own video to make sure that I know exactly where we left off. Okay, because I got everything recorded. So that's the nice thing of having everything recorded. Why did I stash it? 2026 02 02, and that would be, let's see, today is the 12th, so it would be the 10th. And there are two recordings because one is from the time of the lecture recording. Okay, there we go. All right. So let me show you what I have recorded up to the alarm going off. Okay, so this is what I have here recorded. And let me zoom out just a little bit so we can kind of fast forward to the end. So this way I can find out where the end screen is. Okay, so fast forward all the way to the end. Okay, so we did work out all the fractional bit of the mantissa before the alarm goes off. Okay, so we did work out all the way down to F44. There we go. So this is both the nice thing and also the not so nice thing when your professor records his own class recording, because now I know exactly where I left off and I can assign the responsibility to study up to that point to you. All right, so this is where we left off. And that's the last bit, okay, from the leftmost perspective. That is a 1. And then all the other bits from bit 43 to bit 0, they're all zeros, okay, because those are the digits of the mantissa where they are just basically zeros. But we still have to fill up, the remaining 42 bits from bit 43 to bit 0. So that's how we can figure out 52 out of the 64 bits. We know the sign is a 1, so now we just have to figure out the exponent portion. So this is the portion that we haven't really talked about because the 5 is the power of the 2. In other words, this 5 here is the power of 2, which is the same as this 5 over here. But according to the equation, that 5 is going to be this whole big mess here. So that means, the part that is in the parentheses in the sigma notation has to be 1028 because 1028 minus 1023 is the 5 that we actually need. So that's how, this question mark becomes the 1028 because, that's 1028. 1028 is 1024 plus 4. The significance of 1024 is it is 2 to the power of. Hmm? All right, so this is also a good question, that you might need to answer, in order to get a lab done. If I give you a quantity and I ask you, okay, what is the closest power of 2 to that particular number? How do you figure that out? So in this case, I'm asking you, we have a quantity of 1024, and I'm asking you, what is the closest power of 2 to 1024? What is the method to do it? You can, okay, there are a few ways to do it. You can just go through a loop, right? 2 to the power of 0 is 1. Is that close to 1024? No. Multiply that by 2. Now you have 2 to the power of 1, which is 2. Is that close to 1024? No. You multiply 2 by 2 again. Now you have 2 to the power of 2, which is 4. Is that close to 1024? No. You keep doing this until you get to something that looks like 1024. Okay? Is that a method? Yes. Is it really tedious or as tedious as you think it will be? The answer is no, because 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. It doesn't take that many iterations. So for people who decide I'm not going to try this approach, it looks too horrendous to me. Well, I think they're giving up a little bit too early because everything is exponential. Okay, so as it turns out, 1024 is 2 to the power of 10. Let's just say that you don't like this method. Okay, then what do? You go. You can use a calculator. Okay, but how do you use a calculator to figure this out? So what you need to do is to tap really deep into your mind until you find all the algebra stuff that you're supposed to have learned from high school. Hmm? Well, but you don't know the root itself. Okay, we're trying to find the root. So how do you do that? You have to use log. Okay, do you guys remember log versus exponent? That's what you need to use. So I'm not going to teach you guys how to do that because the lab instruction already has instructions of how to do that. Okay. Besides, this is something that you have learned already from high school. Okay. This is algebra. All right. But for the purpose of this part, it's not important because now we know 1024 is 1 followed by 10 zeros in base 2, and then the 4 itself is 100 in base 2. So when you add up those two binary numbers, you end up with this particular bit pattern, which is 1 followed by 7 zeros and then 100 in base 2. Okay? So what is this number? This number, the one that I'm highlighting here, is basically the same thing as f of 52 to f of 62. Okay, so when you look at the bit pattern or the bit field from f of 52, bit 52 of f, all the way to f of 62, those 11 bits would be the ones that we're looking at earlier that is highlighted. Are we good so far? Basically, it is 1 followed by 7 zeros and then 100 in base 2. So now we have figured out every single bit of the double representation of the value that we were working with. All right, so we go back and then we go like, okay, that's exactly illustrating how we will basically fill in the bits, from 52 all the way to 62. Basically, the most significant bit, which is this one here, is bit 62. The least significant bit, which is this particular 0 here, is bit 52. So now we have figured out all 64 bits of the double representation of the quantity that we want to represent, which I believe is negative 58.375. So the most significant bit is the digit, or the binary digit in this case, that is indicating the quantity of the highest power of 2. The least significant digit is the digit that is, in this case, it's basically digit 0. Our digit 0 is the least significant bit. That is correct if we use the normal interpretation, but the equation does not use the normal representation. So if you plug in I equal to 0, what do you get? F of 52. But what do we multiply f of 52 to? 2 to the power of just I, which is 0 in this case. So we take a chunk of bits within the 64 bits, and we just say, okay, look at this chunk of bits as if it is just an unsigned integer by itself. So we have to offset, the bit number in order to get to the power of 2 that is corresponding to that specific bit. And in this case, they're off by 52 bits. Okay, sure. All right. So do we have any questions corresponding, kind of from the formula that we are looking at currently on the projector to the answer that we have already figured out, on the notepad itself? No questions? Okay. So for people who are thinking, gosh, I wish I actually watched the video on Monday before class today, then I would probably be able to catch, the meaning of all of this stuff here. Well, that's okay, because now you know what you need to do for all the future classes, because I can promise you the pace of this class is only going to increase. It's not going to slow down. Okay, so that is important. But up to this point, I think people can still catch up if they put in enough, effort to try to catch up. All right. So now that we have figured out all 64 bits, we need to double check. Okay, we want to double check that the 64 bits that we have figured out, in fact, in a double precision floating point number format, it is actually representing negative 58.375. And the way we do that is to do a little bit of a magical stuff here. Okay, so I'm going to show you this magical stuff. Okay, so at the very top, I am putting in the 64 bits that we have just figured out. The left, okay, let me use a mouse pointer so this way you guys can see which one I'm looking at. Okay, so we are looking at the leftmost bit here, this one here, this bit one. So that bit one is bit 63 because it is the leftmost bit. It is a one because, yes, go ahead. You mean, uh, okay, let me see. I believe there are 7. Yep. So there are 7 zeros here. Okay. So let me just kind of go back and click on this one here. This is our sign bit. Okay. It is a 1 because we need the value that is being represented to be positive or negative. Yep. Exactly. So that's the one that tells me that the the value being represented is negative. This portion here, okay, this is bit 62 all the way down to bit 52. So that is the portion that gives us the quote unquote unsigned number that is biased by 1023. So we take this chunk of binary numbers, convert it into an unsigned integer, and then we subtract 1023 to actually get to the power of 2. So this part is corresponding to, in the diagram, is corresponding to this portion over here. The rest, which is 52 bits, okay, starting from here, all the way down to this zero here. And I even indicate how many zeros there are in the dot 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 notation. So including the first zero and the last zero of the zero dot 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 zero, there are 44 zeros altogether. So that means the highlighted portion here has 52 bits. So that would correspond from bit 51 down to bit 0. Okay? So what do we do with bits 51 all the way down to bit 0 in the formula that we were talking about? Right here, okay? Because if you substitute I being -1, this would be bit 51. If you substitute I equals to -52, this portion would be bit 0. So now we know, which bit is used in which part of the formula that we need to use in order to come up with VD of F, which is the value represented by the bit pattern F. There are 64 bits, but using the double precision floating point number format. So I'm going to pause just to make sure that you guys are catching all of that, what I just talked about, and to see if you have any questions. Any questions? No questions? All right. So if there are no questions, then we go back to the 64-bit representation, and and then the next part here is a conversion table. So when you look at this portion, okay, let me go back one here. Okay, so when you look at this portion here, this is what we call I guess you can call that a binary to hexadecimal conversion table. On the left-hand side, we have 4 bits, okay, going from 0000 all the way to 1111. So that's the entire 16 combinations of zeros and ones you can possibly get when you have only 4 bits. The right-hand side, which is going from 0 to 9 and then from A to F, those are the corresponding base 16 digits of the bit pattern that is on the left-hand side. So that's how you read this table, okay? If you see, I'm just giving you as an example, uh, if you see 1011, okay, it corresponds to digit B in hexadecimal. On the other hand, you can also convert from hexadecimal back to base 2. So if you look at the digit E, it is corresponding to the 4 bits of 1110. Is that okay? So it's a base conversion tool between base 2 and base 16. So between those two bases, there's no need to use multiplication or division of any kind because 16 is a power of 2. That is why we can use a table lookup method to do the base conversion instead of involving division, mod, and crazy stuff like that. This one is just table lookup. Are we good so far? Question? There's no G. Okay, so because we are talking about hexadecimal numbers, so what base is corresponding to hexadecimal number? No. Okay, what is hexa? Hexa is 6. Hexa by itself is 6. What about deci? DECI. That's 10. So what do you get when you add 6 and 10? 16. Okay, hexa is 6. You add deci, which is 10, then you get hexadeci, which is base 16. So this is base 16, and that's why they're exactly 16 digits. No, you're good. So we are converting between base 2 and base 16. The reason why there are 4 bits corresponding to one single base 16 digit is because 16 itself is 2 to the power of 4. And that's why one single digit in base 16 is corresponding to 4 individual binary digits. Are we good so far? Okay. So the conversion goes like this. Okay. We start off with the same bit pattern that we saw at the top, and then we do some reorganizing. Okay. So what I did was to get rid of the spaces, this space, I got rid of this space, I got rid of this space, I got rid of this space over here, because those spaces are only here to help us visualize the different fields or the different chunks of bits of a double, when we are constructing the 64-bit number. But for the conversion process, I have to redivide the bits into chunks of 4 because the table works only when you're dealing with chunks of 4 bits. So that means, when you look at this number here, 1100 becomes its own chunk, and then we have 0000 becoming its own chunk, 0100 becomes its own chunk, and so on. Okay, because you have to group the bits by groups of 4, by blocks of 4, in order to do the base conversion into base 16. Once you have the blocks of 4 bits, then you just look up the table. So we have 1100, the leftmost chunk, and it is just corresponding to C right here, table lookup. We have 0000 corresponding to just a single digit of 0, 0100 corresponding to a single digit of 4, 1101, which is a D, 0011, which is a 3. Originally, we have 44 individual zeros in base 2. So when you block when you put 4 bits in a block, there would be 11 blocks. And then each one of the 11 blocks of 4 zeros would correspond to a single zero in hexadecimal. So this means we have 11 zeros in hexadecimal. So the entire hexadecimal number becomes C04D3 and then followed by 11 zeros. Do we have any questions about the base conversion into hexadecimal? No questions? Okay. All right. So do we actually use hexadecimal numbers in daily life? That means you guys have not done enough networking stuff. Things have been working too well for you, and you have no necessity to have to write down MAC addresses and or IP addresses in IPv6 and that sort of thing. So when you look at any Bluetooth devices or any Wi-Fi devices, the MAC address, which is specific to the piece of hardware that you're working with, is a hexadecimal number. Okay, I'm not sure whether I have. Oh, I do. Yep. So in this case, for this little box here, which is a Wi-Fi extender, the serial number itself is in hexadecimal. The MAC address is also in hexadecimal. So there you go. So it is used, hexadecimal numbers are used quite commonly in all kinds of computer science or computer technology related stuff. And the reason is instead of writing a whole bunch of zeros and ones, you pack 4 individual binary digits into a single hexadecimal digits, so you don't have to write nearly as many digits in order to remember, the unique the unique MAC address of a device. All right. So why are we doing this? We are doing this so that I can check whether this particular hexadecimal number or the bit pattern corresponding to this hexadecimal number, if I interpret that using the double format, that it would actually come back as negative 58.375 in base 10. Okay, so this is what I need to do just to do the conversion, back and forth. So when we look, we can look all day at this number, okay, and go like, what do we do? How can we be sure that, when I interpret the zeros and ones corresponding to the highlighted hexadecimal number, that we'll get back the value that we started off with. So that's when we need to use a particular program. And I just need to find out where I stash that program. Hmm. Okay, well, that's okay. I can, maybe it's not in that window. Let me see which one I'm using. I think it's this one. Okay, there we go. All right, this will work. Okay, there we go. So I wrote a really complicated program called test. Okay, and we'll take a look at the test program here. This is it. Super complicated. Okay, this is the kind of stuff that you learn in maybe week 2 of CISP 360. Okay, so the only thing that is kind of complicated is on line 1, I have a pound include. Okay, that pound include is not including standard IO, it is including standard integer.h. So what that is helping me to do is it is importing a bunch of type defs or type definitions. A type def in C++, can somebody tell me what is a type def in C++? Did you guys learn that concept in CISP 360? No? Okay. So what did you learn in CISP 360? Okay. A type def is an alias, okay? It's basically an alias of a particular type. So in this case, the alias, which is just another name, is uint64 underscore t. It is one of the many aliases defined in standard integer.h. So can someone guess this is an alias of which type, or what is the type that this is indicating? Yep, it is the alias of a unsigned 64-bit integer. Okay, so this means x is variable x is a fixed width binary number that is using exactly 64 bits. Now, yes, go ahead. That's just part of the name. Yep, because underscore is usable as a part of an identifier in C++. So in this case, that's just part of the standard of using underscore t to kind of emphasize that this is a type def. This is the alias of a type. Before I go any forward, does everybody understand what alias means? ALIAS. Yes? Shucks. I was about to give you guys a really funny example of an alias. I'm gonna use it anyway, okay? Bad Bunny. Bad Bunny is an alias because I cannot imagine any mother who would call his son, "You are Bad Bunny." Okay, so Bad Bunny is an alias. Okay, it is just a name that we use to call someone when that someone actually has a real name. So, what is the actual real name of Bad Bunny? Nobody cares and nobody knows. Okay, but now I'm curious. Hmm? Not that I can reproduce that. Okay, we'll look it up. What is the real name of Bad Bunny? Benito Antonio Martinez. How do you spell the last name? Ocasio? Okay, cool. And he looks kind of pretty okay and normal in this picture. And then this is a entirely different kind of person. I think the glasses makes a difference. I think I need new glasses, don't you think? Yep, I think so. All right, cool. So anyway, you can see that this program doesn't do anything, right? It assigns a 0 to x and then just returns 0. That's it. So as it turns out, line 5 is actually necessary, okay? If I take out line 5, the compiler would actually optimize the variable x out of existence. Then I cannot really do what I need to do. So I actually need an assignment in the program to make sure the compiler does not optimize x as a variable out of existence. So anyway, so you look at this program, you go like, but what about that constant that we were talking about? It's not even in the program. What is the purpose of this program? All right, so we'll see what we're going to do with this. So we'll go ahead and compile this program. And I'm a command line kind of person. So this is how I compile a program. You will see me using a compiler, on the command line and also using GDB on the command line quite a bit in this class. So this is how we compile the program using, including debug information. That's what the dash G is for. And then the dash O tells the compiler the output should not be named a.out. It should be named test. Okay. So those are called switches on the command line. All right, so we just compile, and then we use GDB to debug the program. So when you use GDB, it has a whole bunch of commands, and they're all kind of on the command line. I'm so used to this that I don't want to use anything else. So we have to put a breakpoint on line, let's say line 6. Does everybody understand what is a breakpoint when you're using a debugger? The concept, okay, not so much the command to put a breakpoint on line 6, which is B6, which is break 6, okay? So the concept of a breakpoint is okay. So it means the breakpoint will be triggered on line 6 before the execution of line 6, okay? All right, so we put a breakpoint in, and then we run the program, and now the program has just run and has paused because I just get it to line 6. So this is where the fun begins. Because at this point, I can say, okay, tell me what is in X. Not exciting, right? But I can also do a set var, set variable X to the 16-digit hexadecimal number that we just worked out. So now we just go to we go here, and then we say copy, we switch back here, and then we just paste it here. There we go. All right. Press the enter key. It doesn't give you any feedback because it just says, okay, if you want to change X to this this these 64 bits, we'll change it to these 64 bits. And then we'll print it. So when we print it, okay, you go like that's nowhere close. That's not even close to the number that we are thinking about. You are correct. So what exactly are we looking at here? What is this crazy long integer representing? It is not some integer. This is actually VU in parentheses F comma 64. Okay, so I'll type it. Okay, I'm not sure, I can only type it, but I can't, really turn it into comments. So I have to undo it later. So this is F, no, excuse me, V underscore U or subscript U, open paren F 64. That's the value. Okay, so this is a quick quiz. Okay, you guys are gonna get your exam one in about 2 weeks. I might as well help you study by shocking you. It's like, what is VU of something? Because you're gonna need that in order to get the exam done. So what is V underscore subscript U F64? Okay, so let me say V subscript U open paren F64. What does it mean? Okay, one hint, it is not the name of one of the children of Elon Musk. Hmm? Exactly. This is the value, this is the unsigned in the, okay. how should I put it? This is the least significant 64 bits of f interpreted as an unsigned integer. Okay, that would be the best way to put it. And if you don't remember how it is defined, I urge you to find out how it is defined. Okay, because if you have been following my advice, okay, you would have the definition of all of these things, somewhere on your own piece of paper at a corner, because that's what I have been trying to tell you guys to do. Okay, the definitions are important. Okay, write it down so that you'll forget, or you don't have to look through my notes to find out how they're defined. So I will let you guys find out how it's defined, but it's basically looking at the same 64 bits that we're looking at, but interpreting bit 0 as the quantity of 2 to the power of 0, bit 1 as the quantity of 2 to the power of 1, and all the way to bit 63 being the quantity of 2 to the power 63. So when you add all of those powers of 2, that's what you see on the screen as $2. Okay, so when you look at $2, that's the interpretation, which is not what the value that we're looking at. So in GDB, you can also print using hexadecimal. Okay, so if you do a slash x, it means, okay, I don't like decimal representation. I want hexadecimal representation. That's what the slash x is doing. So when we do this, then we get the same 16 hexadecimal digits back, okay? Because we are just changing the format. We're changing the base, okay, of how it outputs the same value, which is also not what we're expecting, right? Because we want to get back negative 58.375. That is not it, okay? So some of you are now thinking, maybe we need some casting, okay? Okay, so I can see people nodding, but I do have to ask, do you guys remember what is type casting from CISP 360? Hmm? Maybe that is okay. All right, so typecasting is essentially telling the compiler, change the type to something else. Okay, so we'll go ahead and say, okay, oops, not float, double. There we go. So what this is saying is, hey, debugger, but this works in the compiler as well. It is basically saying, hey, compiler, look at the value of x, okay, and then convert that value to a double, so that I can use, sine, cosine, and all the other, math functions. Okay. So you go like, well, this is going to work, right? Because we are talking about using a double precision floating point number interpretation of a particular bit pattern. And this is going to take the value of x and turn it into a double. Isn't that the same thing? The answer is no. What I just said are two different things. Okay. Let me separate those two for you. The first thing that I said was, um, take the 64 bits in X, interpret those 64 bits using the double precision floating point number format, which means I'm taking bit 63 as the signed bit, I'm taking bit 52 to 62, the unsigned integer thereof, as the biased exponent, and I'm going to take bit 0 to bit 51 as the fractional part of the mantissa. That is reinterpreting the bit pattern. The second thing that I said, which is what this expression is doing, is to take the value of x and turn that type into a double. In other words, I'm already using VUF64 before the typecasting happens. So it's not going to help me much, okay? So I can press the enter key and you can see kind of like, oh, that is not helpful, because you can see that it's printing exactly the same value, except this time it is in the format of a scientific notation, okay? This is a scientific notation that basically has a mantissa of 1.3856 blah, 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 in decimal times 10, to the power of 19, which is approximately the same thing as what we saw with $2. It's approximate, it's not exactly the same, because I think somewhere along the line we lost 3 digits. Where is the least significant 3 digits? 472. It's gone. Okay? It's gone because in order to represent this many digits in decimal, we pretty much have to use every single 1 bit of the 64-bit unsigned integer. The mantissa by itself has how many digits in a double? You can include the 1 point, okay? So including the 1 point of a double, how many bits do we have to express the mantissa of a double? It's 53. It's 53 because we have 52 bits to the fractional part and then plus the 1 point. So we have a total of 53 bits, which is still falling short by 11 bits compared to a 64-bit number. And that's why the precision of the mantissa of a double is actually less than a 64-bit unsigned integer. Okay, we're losing some precision here. All right, but the bottom line is this trick also does not work. So I'm going to give you something that gradually will point to the uh, the thing that we need. Okay, what is this? What is the ampersand? Yep, address of. Okay, the ampersand operator is the address of whatever is following the ampersand or the single ampersand. If you do not know what is the ampersand operator, it is time for you to study the ampersand operator because we'll be using it quite a bit, okay, along with the other operator that we'll also be talking about. So this is taking the address of the variable x in this case. If I press the enter key, it will give us something that is not terribly exciting, okay? It is simply telling us that the address of variable x is at location. Once again, we have a hexadecimal number because it has a prefix of 0x, okay? So in C and C++, 0x is the prefix of a hexadecimal number, okay? So in this case, the address turns out to be 7FFF FFFF DD56. Okay, it is some location in RAM. Okay, okay, not particularly exciting. Okay, so the question is, but why do you want to take the address of X when what we really want to do is to change the interpretation of the 64 bits of X, so that we can reinterpret it using the double format. So what about this? What is that going to do? This is typecasting, but what are we supposed to get as a result of this typecast? What am I casting? Yes, exactly. I would get the same address, but the output would say it is now the address of a double instead of the address of a 64-bit unsigned integer. So I'm basically rezoning in this case. I'm not changing the address. I'm not changing what is at the address. I'm just rezoning that particular address. Okay, so go like this. Okay, yes. Aha. So asterisk means, okay, can somebody help me with this one? Dereference. Okay, well, okay, there are several ways to look at this. In the case of a type, okay, you can interpret the asterisk as a pointer to whatever is on the left-hand side of the asterisk. So when you see this, as in a type setting, which it is now, it is basically saying whatever this number is, 0x7FFFFFFFDD58 is the address of a double. You can also see it as a pointing or pointer to. So that means, 0x7FFF, blah, 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 is pointing to a double. So they mean exactly the same thing. Okay, very good. So you look at this and go like, okay, we're just running around in circles, okay, because we're still looking at an address and how is this going to help me? Well, what about this expression here? What is this particular asterisk going to do in this expression? Hmm? This is called dereference. Okay, so this means in the very same expression, I am using address of, and then I'm using dereference, which normally is a stupid thing to do because dereference kind of cancels out the address of thing, so they kind of like combined. They don't do a single thing, except in this case, between the two, I have a typecast. Okay, so that is the trick. Okay, that is the trick that works. Okay, because when I press the enter key, you go like, how, what, how did we get back to negative 58.375? Because step by step, the ampersand says, okay, give me the address of the 64-bit unsigned integer that is holding the 64-bit pattern that we just worked out. So that gives me the address of an unsigned 64-bit integer. The typecast, which is double asterisk, is saying, well, I know what I'm doing, so look at this address as the address of a double. Okay? So with that typecast, okay, so if we look at just this portion here, that becomes the address of a double. You go like, but it wasn't the address of a double. Yeah, but I convinced the C compiler that I know what I'm doing. Just look at it as the address of a double. And then what do I do with the address of a double? I do a dereference. Okay, go to that address, get those 64 bits, and show me the value of that thing as a 64-bit as a double. Okay, so now it's interpreting the very same 64 bits that we put in as an unsigned 64-bit integer, except this time it is interpreting all those individual bits, the very same 64 bits, now as a double. Are we doing okay so far? Okay, so this particular trick is a little bit tricky, okay? But it is not to the point where someone who has taken CISP 360 cannot understand. Now, can I expect you guys to come up with this trick? No, I would not do that, okay? But once I explain it, okay, which part is which part, do I expect you to understand how it works? I do expect you to understand how it works, okay, because that really is a part of C++, and I'm only using things that you should have learned in CISP 360. Are we doing okay so far? But the key is we got back the value that we were using on Tuesday to come up with the bit pattern to begin with. So are we doing okay? All right, cool. So I'm going to reverse the whole thing, and this time we're going to have to go back, we have to go backwards, okay? So this time what I'm doing is I'm going at this pattern here, and I'm changing this a little bit here, and I'm going to change this to, instead of a D3, I change it to a 3D, okay? So I just changed the bit pattern a little bit, and what I want to do this time is to figure out what is the actual value represented by the new 64 bits in this double. Are we good? Do we understand what I am trying to do? Okay, so I'm trying to reverse the whole process. So I press the enter key, nothing happens. Now, obviously, if I just kind of go back to this point and press the enter key, I would know the value that it's representing, but that would defeat the whole purpose of what I'm trying to do. So what I would do is to reverse the whole process by hand without using a calculator. Okay, so I'm taking 64 bits, okay, 64 zeros and ones. I actually have no idea what value is representing. I have a general ballpark, but not exactly. Okay. And I want to reverse the whole process and say, okay, what exactly is the value represented by this particular bit pattern? So what I need to do is I'm now taking this here, okay, right click, copy it, and then switch back to my editor. So on the other day, I chose another bit pattern to work with. So I'm going to take this out entirely because I'm going to work with this number now. Okay. So the first thing I need to do is to unpack all the bits. In other words, I go from base 16 back to base 2 so I can single out individual chunks of bits. Okay. So now I just look at a 4 is a 0100, a 0 is 0000, a 4 0100 again, a 3 is 0011, a D is 1101, and then I just have a whole bunch of zeros. So there are, once again, 64 zeros, or 44, sorry, 44 zeros after that. Okay, so once I have this, I pack everything and then I chop it into the actual fields that I need. Okay, so I have to chop the 1 bit out and then another 11 bits and then the remaining 52 bits. All right, so I can do this. Okay, here we go. And then I take out all the spaces. Okay, the last portion is not too important. I can kind of not have to do anything about that. So I concatenate all the bits back together as one single chunk, and then I single out the bits. This is bit 63 in a double precision floating point number. It is by itself because it is the sign bit, okay? And that's why it is kind of separated from the rest. We know the exponent is specified by a 11-bit unsigned integer, so I have to kind of chop that out too. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have to now take this chunk out. Okay, something doesn't seem right. Okay, I think I miscounted. There should be 11 bits. Let me count it one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. So the boundary is right here. And then the rest are the fractional bits of the mantissa. Are we doing okay so far? Okay. So if you're thinking, this sounds like kind of what we did on Monday, except everything is kind of flowing backwards, then you'll be correct, okay? Because I'm just reversing the entire process. All right, so what do we do now? Well, the first thing we know is f of 63 is a 1, is a 0. So that means whatever the value is non-negative, okay? So we have non-negative value, okay? Very good. And then when we look at f of 62 all the way down to f of 52, that is 1000, 1, 2, 3, 4, 100. So that is the same number that we had before because I didn't change this portion. So that would be 1028. But the biased, okay, this is the unbiased, excuse me, I take it back. This is the Yeah, this is the biased exponent, which means it is off by 1023. So the actual unbiased exponent is 1028 minus the bias amount, which is 1023. So now I have to say the exponent of 2 is 1028 minus 1023, which is exactly 5 because that's the same as last time. And now we have the mantissa. So the mantissa is 1 point, and then the whole bunch of bits that we work out, okay? Because we have to remember the 1 point, the 1 point is not a part of the representation. It is just going to be there all the time. Okay, we talked about this on Tuesday as well, okay? Because we were talking, so that would just be this chunk of bits here. Just do a whole bunch of copy and paste, like so, okay? And we have to remember it is a base 2 number. Are we still doing okay so far? Okay. So now what I need to do is to say, okay, the actual value that we are looking at, okay, the value that we are looking at is the mantissa, whatever that thing is, times 2 to the power of, in this case, 5. So that means, we just have to kind of copy and paste one more time. Okay, take this whole thing here, stash it over here, times 2 to the power of 5, and now we have to figure that out. And I did say something about not using a calculator, so I'm not going to use a calculator. And trust me, this Bluetooth is only for recording purposes. It's not like somebody outside is reading me, any one of these numbers. If you don't trust me, someone can walk outside and make sure that, within the Bluetooth range, which is about 30 feet, there's not another person, kind of talking, Tack, this is the answer. Okay, so how do we do this? There are a few ways to do it. I hate working with very negative powers of 2 because, those are not very nice base 10 numbers to work with. So what I'll do is exactly the opposite of what we did on Tuesday, okay? Which is to say, hey, this is a 2 to the power of 5, so that means I can shift the 0 or shift the point of the mantissa 5 times, but this time to the right-hand side, and then get rid of this one here. So this will turn into a 0, but I have to move this point exactly 5 times to the right hand side. So that will be 1, 2, 3, 4, 5. So put the period over here, and now this equality is holding. Okay, by the way, this equality right here, that is holding because for every shift of the binary point to the right hand side, I have to decrease the power of 2 by 1. Okay, for the same reason that we have to increase it by 1 on Tuesday. So you can see that I'm actually referencing things that I talked about on the previous day. So that means, this is why I ask people to review the material of a previous lecture before the lecture of the day. Okay, because that actually is important. All right, so now we go like, okay, that's pretty cool because, what we can end up here is to say all of this stuff here is useless. Just take that out, okay? And this is all we are left with, which is a base 2 number. And now we are just using the base conversion thing that we talked about a few weeks ago, like 2-ish weeks ago, about the base conversion, and convert a base 2 number back to the value that it is representing, which is not too terrible in this case because, this one that we're looking at here, that is 2 to the power of 5. Okay, so that's a 32. There is no 16. There's no 8. There is 1 4. There's 1 2. There's 1 1. There is a half, and there's a 1. There's 1/8. So we just have to add these two, add this number together, and I can see. Okay, cool, cool. 4 plus 2 plus 1 is just 7. 32 plus 7 is 39. And then 5.5 plus 0.125 is just 0.625. Okay, so 0.625, and that should be the answer. Okay, so that kind of not so random, but different bit pattern that I was using earlier should be interpreted using the double precision floating point number format. It should be interpreted as the value of positive 39.625. Nope. The next the next 11 bits are the is the exponent. And then you subtract 1023. Yeah, so the key is to, okay, I have no idea where my browser is in the tabs, but there we go. All right, so you basically have to look at this and annotate this, okay? And basically go like, okay, if I equals to negative 52, this is bit 0. If I is -1, this is bit 51. So this is the portion that makes use of bit 0 to bit 51. If I put, I equal to 0 to this I over here, this is bit 52. If I say I equals to 10, this is bit 62. So this is the portion that makes use of bit 52 to 62. And then bit 63 is by itself over here. So it is important to kind of have your own notes, okay, so that you can read about it. You can make a picture too. I mean, you can just kind of make a picture. You can use color coding, but the key is you have to um, record this in the format that makes sense to you. Okay. All right. So I made a claim. Okay. This is the claim that I made. The value that should be represented is 39.625. So now we can go back to the debugger, and I use the same expression to double check. 39.625. Okay. So I'll be doing okay so far with the process. Okay. Because the process is, I did not invent the process. Okay. So let me ask you this question. Okay. How did you think that I derived the process that I just went through between today and Tuesday? Okay. Option number one, Tech is reading this from somebody else's, video on YouTube. That would be too much work. Okay. So how do you think I derived this process? By understanding the formula. Okay. So the key is the definition. Okay. The definition is the starting point because in this particular case, if you know this definition, you can derive your own process. The only thing that is a little bit tricky is the base conversion part, because without the base conversion part, I cannot get the debugger and I cannot enter the 64-bit pattern into the debugger and then use the debugger to help me reverse back to the value as a verification process. So that's the only part that is, I would say, a little bit on the tricky side, but not terribly tricky. Question? Nope. Okay. All right. So that is pretty much all I want to talk about in double precision floating point number. So you would say, but what about the rest of this entire chapter or the entire reading module? Well, there was one time that I would actually expand double for this particular module to also talk about conversion between base 10 and base 2. In other words, you can give me a base 10 scientific notation, and there's a process to convert that into a base 2 scientific notation. In other words, when you have a C in and somebody type in a um, base 10 scientific notation, it has to store that base 10 scientific notation that you type in. Internally, it has to store as a double, which is essentially a base 2 scientific notation. So the question is, how does that magic work? Do we understand enough math to actually make it happen? So as it turns out, the answer is yes. Okay, it's a rather tedious process, and there's some math trick to it. Okay, but when I say math trick, I'm talking about division. I'm talking about taking the floor of something. So I don't think it is something that is outside of what we can do in this class, but I got more important stuff that I want to spend more time on, and that's why I don't kind of cover the rest of the module anymore, and you don't have to worry too much or worry at all about the rest of this module. Okay, so up to this point is all you need, and it's 42, so we still got a little bit of time. So I'm gonna go back to, where is it? You I think it's over here. There we go. All right, so I do want to go back to the announcement because I just sent you guys a particular announcement, which is the the test last semester. Okay. Um, so when you open this, this is the actual exam one from mm, fall 2025, the previous semester. So your exam is coming up. Okay. So I will go over this test next week, and then your exam is going to be 1 week after that. So I'm going to say that your exam is going to be um, the Tuesday after next Tuesday. Okay, can someone give me a date? I can just find it myself too. Give me a second. Give me a second. All right. So next Tuesday is the 17th, and the Tuesday after that is the 24th. So February 24th is going to be your exam one. So make sure that you have it marked down, on your calendar. And this is the test from last semester. And I have a nasty habit of not using the same questions between semesters. If I can have my way, I would never, ever reuse any exam questions in my entire career. I think that's almost possible because I'm retiring in only a few years. So I think I can keep that up for another few years. Yes, I don't know yet. A few people in this class were also in my CISP 440, so they're used to this kind of answer from me when people ask me, so what is going to be in the exam? I don't know. I know the scope of what I'll be asking, but I don't know exactly what question I'll be asking because I don't have the questions yet. hmm All right. So with 5 minutes remaining, I'm just going to give you a quick tour of this particular exam, just so that we know, you know, next Tuesday we'll be talking about this. But before we say, okay, that's fine. We'll get to this part, and then I'll give you replace that and open it up again, like so. There we go. All right. So the first question, I spent a lot of time to design these questions, and they are really, really great because I can generate enough variations of each one of these questions. So in a class, especially when there are only like 20 something people, no two students will have exactly the same question. I actually wrote programs to do that. Yep. All right. So, what is this about? Okay, so when you read this and you go like, okay, I can kind of know what this is about. Line 1 is telling me that T2 is not X1 and Y1 or not Q1 and T1. So if you can read that part, you're good with at least understanding the symbols. Okay? So the next thing is, but what does that mean? What is T of 2? When did we talk about something that looks like T subscript 2? Binary subtraction. That's exactly it. But in binary subtraction, we have T of 2 that should equal to B of X1, Y1 or B of Q1, T1. So how do we end up with not X1 and Y1? Because that's how the function B is defined. We talked about all of this already. So if this is looking foreign to you, it just means that you might need to study a little bit, okay? You have to go all the way back to the definitions, okay? Especially the definitions that are applicable to base 2. So you have to go study, okay? Now, the exam is open book and open notes, okay? But I do have to, just out of my own integrity, I have to warn people and say that just because it's open book and open notes does not make it easy. Okay? Because the amount of time for somebody who did not study at all to find all the definitions in order to understand what this whole thing means, is going to exceed the entire exam time already. So open book and open notes does not help people who did not spend the time to study and to understand the material. So I just want to warn people because um, for this class particularly, because somebody can just take 300, 360, and then come to this class. 440, not so much. Okay, most people in my CISP 440 class, the moment they hear open book and open notes, they go like, ugh, not one of those, because they understand that if it's open book and open notes, it has nothing to do with whether you can remember things or not. It has everything to do with can you apply what you have learned to potentially solve problems that you have not seen before. Okay, as opposed to, oh, I just want to see if you know what this means. I mean, are you guys sufficiently warned? Okay, very good. So this is question number one. Read the question itself, find out what it wants you to do. Okay, this is really super duper important. And then we will move on to question number two. So question number two is, okay, if you read part one, it refers to VUPW. Okay, so right away, okay, you know that you need to remember where to find the definitions. Okay, if you cannot remember the whole thing, it's okay. Okay, you just need to kind of have it in your notes somewhere. And by the way, open book and open notes does not have a limitation, especially when we're in this classroom. Okay, this classroom can accommodate at least 60 people, 60 people. Okay, so on the day of the exam, I don't want people to be sitting like right up next to each other. I need people to kind of space out a little bit, but it also means they can bring a lot of stuff with you. Okay, does it really help when you bring a lot of stuff? Nope, because you have to search through all that stuff. Okay. Okay. Now you can bring a lot of stuff. Okay. But if you have your own notes and you have everything that you need in your own notes, that means the rest of the stuff is a backup, right? Just in case you did not write down something, you know that if you print out my modules, it'll be there somewhere. Okay. It's a good backup. Do you guys remember that I'm asking you guys to write your notes or take notes in this class? Like every single class, I repeat that at least like 3 times. Why do you think that is important? Because that is your study guide. I don't give you a study guide. I don't know how you study. How can I possibly give you a study guide if I'm not you and I don't know how you study? Your notes is your study guide. Okay. Now, some people go one step further. Okay. They don't just take notes in the class. After the class, they read all the notes, they read the reading material, and then they refine the notes that they take in class into something that's even more refined. That is your study guide. Okay, so you should have been working on your study guide this whole time. Okay, is that making any sense? Okay, now if you want to take that one more step, okay, which you can, is to condense that study guide to something that's even more concise. Because the more concise the study guide, the quicker you can find your stuff. And every single time you refine your own notes into your study guide and you refine the study guide itself into a condensed form, guess what you were doing? You're studying. Okay? But you're studying in a way to produce a deliverable you can actually take with you to the exam. So you would have been helping yourself the entire time if you kind of follow that process. Does that mean everybody has to do all of this and bring in, notes and whatnot? No, I have had people who just kind of walk in with a pencil, okay, and ace the exam. Okay, but do I encourage you to kind of go like, maybe I'm that person? Well, it's kind of like, me going to an NBA tryout. Okay, I'm gonna give you that analogy. Okay, the chances of me, getting, is it called selected or qualified to be an NBA, to get it to even be drafted, would be about the same probability of a student in this class coming to exam one with a single pencil and be able to ace the exam. So I'm gonna give you the probability, the chances, the odds. All right, so this is question number two. We are already out of time, so do this test, okay? We have a long weekend. I know from this class's perspective, we do not, but since most of you are taking classes on Monday, you're still extending the weekend by at least one day. So use the long weekend to work on this exam. Okay. Now, because it's open book and open notes, so don't try to remember things. Okay. If you need to look up something, look up that something, spend the time to understand that something in order to try to answer the question. The more time you spend to try to understand the material, to try to answer these questions, the more the explanation will make sense next Tuesday. Okay, so that's what we'll be doing on next Tuesday is to go over the answers to this particular quote unquote practice exam. We do have a lab today, okay, because I got one planned on the other day already. So let me take a look at the access code. All right, so this is going to be float. Okay, so today's lab is floating point one. Go and oh, by the way, one for once, okay, there will be instructions associated with the lab tonight that may be important. Okay, if you cannot remember all the log stuff that you're supposed to have learned in high school, remember algebra that we talked about earlier, that might be actually be helpful. Um, and then tonight's access code is not very creative. It's IEEE, the International Electrical and Electronic Engineer Organization. All right, I'll see all of you in STEM 301.